Okay, so over the course of the polynomials chapter so far, we've really focused on polynomial algebra. So building up the tools to be able to factorise a polynomial and hence being able to solve a polynomial equation. Now, when we're talking about polynomials here, we have talked generally about what a polynomial function is, but in terms of practical calculations, we're really just focused on cubic and quartic functions. Obviously, linear and quadratics are also polynomials. We've dealt with them specifically in separate topics. And we won't really talk much beyond, degree 4 polynomials in terms of the specifics, although I will touch on that as we go through this video. So what we now want to be able to do, now that we've got the algebra behind us for working with polynomials, is we now want to be able to sketch polynomial graphs. And we obviously know that when we sketch a graph, we inherently need to understand the algebra around the function in order to find intercepts and other key features of the graph. So what we want to look at in this video is we want to start off by looking at the most basic cubic graph, and that is y equals x cubed. Okay, so let's just focus on plotting out some points and getting a sense of what this is going to look like. So let's start in the middle, because when x equals 0, that's the easiest number to sub in here. When x equals 0, y clearly will equal 0. 0 cubed is 0. When x equals 1, let's go to the positive side now. When x equals 1, y is equal to 1 cubed, and 1 cubed is also 1. When x is equal to 2, y is equal to 2 cubed, and 2 cubed is 2 times 2 times 2, which is 8. And when x is equal to 3, y is equal to 3 cubed, which is 27. Now when we cube negative numbers, remember when x is equal to negative 1, it will be negative 1 cubed, which means it's negative 1 times negative 1 times negative 1. Negative 1 times negative 1 gives us positive 1, but then we multiply that by negative 1 again, and so we still end up with a negative answer when we cube a negative number. I know that tripped up a couple of you earlier on in this topic when you were doing some of the work. So negative 1 all cubed will be negative 1. Negative 2 all cubed is negative 2 times negative 2 times negative 2, which will be negative 8. And negative 3 all cubed will be negative 27. Okay, so let's think about plotting those points. Some of those points won't fit on this particular axis we've got, but that's okay. It gives us a sense of where the graph is heading. So we go through the point 0, 0, we go through the point 1, 1, we go through the point 2, 8, and then 327 is way off the chart. Okay, so it's clearly shooting up quite quickly. Negative 1, negative 1, negative 2, negative 8, and again, negative 3, negative 27 is way off the chart, so we get that sense that it's really getting very steep. And so if we join these points up, we actually get a graph that looks something like this. Let me fix that. And this is the graph of y equals x cubed. Okay, let's also establish the basic shape for y equals x to the power of 4, and then let's put that together with what we talked about when we applied transformations to a graph, when we talked about that back in the parabolas topic, y equals x squared. And if need be, you can go back to have a look at some of those transformations of the parabola video, but I will touch on that. I'll jump across to a graphing program in a minute. So let's establish the basic graph shape for the quartic. Actually, before we do that, let's just talk about the cubic, because there's actually a new graph feature here that we haven't met. Okay, and that's what's happening at this particular point here. And this is called a point of inflection. Okay, so it's a point where the graph sort of bends but doesn't actually turn around. So this is actually a particular type of point of inflection. It's a stationary point of inflection. And that is, so a point of inflection is where the graph bends. So we can just have a point of inflection that does something like that. But this is a particular point where when it bends so that the gradient is 0. So it actually momentarily gets flat, just for a moment, and then gets steep again. So if you were to draw the tangent to the graph at this point, it should be a nice horizontal line. Whereas if you were to have a non-stationary point of inflection and you drew the tangent at that point of inflection, it wouldn't be a horizontal line. By definition, a point of inflection is a point where, if you were to draw the tangent at that point, so a tangent being a point that has the same gradient as the line at that point. We've talked about tangents a bit more in the context of circles rather than curves. But if we were to draw a straight line that has the same gradient as the curve at that point, for a stationary point of inflection, the gradient is 0, and so we get a horizontal line. but for a non-stationary point of inflection, the gradient won't necessarily be 0. But the point is that when you draw the tangent at a point of inflection, the tangent actually cuts through the graph at that point. So we see over here it's above the graph, it touches the graph there, and then it's underneath the graph. Okay, here it's above the graph, it touches the graph there, and then it's underneath the graph. Okay, so that's what makes something a point of inflection. And in particular, the cubic has a stationary point of inflection. So when we draw the shape, we want to try and get that sense that for a moment, we get a moment of zero gradient, just like we do with a parabola, zero gradient, but then it turns around. But here we get a moment of zero gradient where it then starts to go back up again. Okay, or, you know, obviously we can talk about reflections, but it will go this way. So we do want to get that sense. Okay, so then we have a look at the quartic function. So let's plot out some points for that. So let's again start in the middle. When x equals 0, 0 to the power of 4 is clearly still 0. When x equals 1, 1 to the power of 4 is clearly still 1. When x equals 2, 2 to the power of 4 is 2 times 2 times 2 times 2, and that is 16. And when x equals 3, 3 to the power of 4 is 3 times 3 times 3 times 3, and that's 81. So again, when we think about the negatives here, if you have negative 1 all to the power of 4, you've got negative 1 times negative 1 times negative 1 times negative 1. So multiplying the first two together give you positive 1. And then you multiply with the third negative, and you get negative 1. But then you have to multiply by negative 1 again, and so you end up again with positive 1. So if you have an even number of negative numbers multiplying together, you're going to end up with a positive. So that's why when we square a negative, we get something positive. When we raise a negative to an even power, so to a power of 4, we'll get something positive. So this will also be 1, 16, and 81. Okay, so we get that symmetry in the x to the power of 4 graph, like x squared, that we don't get with x cubed. Okay. Right, let's plot some points. So we go through 0, 0, we go through 1, 1, we go through 2, 16, okay, and then 381 is way off the charts. Negative 1, 1, negative 2, negative 2, 16. Okay, I just want to think a bit about how this is different to the parabola before I draw in the shape. So the parabola goes through 0, 0, 1, 1, and negative 1, 1 as well, but it only goes then through 2, 4, and 3, 9, okay. Negative 2, 4, and negative 3, 9. So it's much less extreme. Okay. Obviously, raising something to a power of 4 is going to mean that it gets big much quicker. The other thing that's interesting, let me just roughly draw this in. You don't need to draw this in on your graph. Just watch for a minute. Is that if you were to think about what happens between 0 and 1. So if you think about, for example, when x is a half. If you have half squared, it's going to be a quarter. If when we draw in our degree 4, our quartic polynomial, if we do half to the power of 4, it's not just a quarter, it's 1/16. So it's going to be a lot lower down than this. So for the fractions, they're going to be much smaller, and then we see that it gets big much more quickly. Okay, so we get big really quickly, but then we also slow, let's try that again. We also slow towards the x-axis quite quickly, so we get there quite quickly, and then obviously so we get this sort of, compared to the parabola, it's a more flat-bottomed shape. So, you know, if we were going to be extreme about what's happening here, we have parabola, we have cubic, we then have quartic with a slightly flatter bottom. And I'll have a look in a minute at what happens with the higher degree polynomials, but we would find these two shapes essentially just get more extreme. So the quartic, you know, degree 6 would be even flatter and steeper. Degree 8, obviously it's hard to draw that. So, you know, if you've got a parabola and they intersect here and here and here, and then you've got the quartic is going to be steeper than that and then lower down than that here. So you get the sort of squarer shape. And then degree 6 would be even more extreme, and degree 8 even more extreme, etc. And the same thing will happen with the cubics. So if this is a cubic, degree 5 is going to be more extreme, okay, etc. So I'll show you that in a second once we have a look at transforming these shapes around. So the quartic graph still has a turning point. It's not a point of inflection, so like the parabola, it has a turning point, it's symmetric, and obviously like any other graph, calculating x-intercepts and y-intercepts, and in the case of the quartic, turning point; in the case of the cubic, the stationary point of inflection. They are key features that you would want to label on your graph. So now let's think about applying the transformations. Okay, so I'm just going to skip across to another program for a second. Okay, so here we're going to start with what we know. So this is our parabola, y equals x squared. So at the moment we've got, it's actually a times x to the power of n, but n is 2, that's why we're seeing the parabola. And remember, if we talk about a times x squared, so that's, remember, about dilating from the x-axis. So if we were to change the value of a here by making a bigger, we see that the graph stretches away from the x-axis. We also know that a can have an effect of reflecting in the x-axis if a is a negative number. Okay, so if a is a negative number, down here, our graph is going to be reflected in the x-axis. So we're just taking whatever the basic parabola shape is, and we are stretching it away from the x-axis by a factor of a, and if a is a negative value, we are reflecting it in the x-axis. So now if we change the value of n to make it 3, so we're looking at the cubic shape, and then we play around with a still has the same effect, which is to dilate the graph from the x-axis by a factor of a. Okay, so here, for example, is where a is 3. If we look at the y coordinates of each point, they are tripled. So instead of going through the point 1, 1, the graph that's dilated by a factor of 3 from the x-axis now goes through 1, 3. Instead of going through the point 2, 8, this graph would be going through the point 2, 24, which is off the screen here. Okay, so we've stretched it away from the x-axis by a factor of 3. Obviously, if we make a fraction, the graph gets squashed towards the x-axis. If a is 0.5, we're halving all the y coordinates. So instead of going through 1, 1, we go through 1, 1 half. Instead of going through 2, 8, it now goes through 2, 4. And if we were to continue to decrease a until it becomes a negative value, we see that we now get this reflection in the x-axis. So there a is negative 1. So this is just directly the graph of y equals x cubed reflected in the x-axis. So a still has those same two effects on the graph, to stretch it away from the x-axis, or towards the x-axis if the scale factor is a fraction, and to potentially reflect it if a is a negative value. Okay, let's think about this version. So, oh sorry, I've lost my information here. Let me just get that happening. Okay, so let me just make that a little bit more legible for you. My apologies. Let's put it in red so we can see it. Let's make it a bit bigger font. Okay, so we're looking at here the graph of y equals x minus h to the power of n. So at the moment, n is, on this particular graph, sorry, let me get this up again, n is currently 2. And so we're seeing a parabola, and we know that as we change the value of h, now given how it's set up here, x minus h, if I make h bigger, the graph is going to go to the right. So let's have a think about it. Let me make h 2. So now we're looking at the graph of x minus 2 all squared. It's gone to the right by 2. So remember, when it's minus inside the function, it goes to the right. And if we were to make h something negative, so if we make it negative 1, for example, this is the graph of x minus negative 1, so x plus 1 all squared. So when it's x plus 1 all squared, it goes to the left by 1. Okay, so now let's see if we change the power if we change the power to 3, for example, we've got the cubic, and then if we change the h value, the same effects happen. X minus a positive number moves it to the right by that amount. X plus a number, so in this case it's minus a negative number, which makes it x plus a number, makes it go to the left. Same shape, all we're doing is translating it to the left and to the right. Okay, I didn't have a look at the quartic on the other graph, but let's have a quick look. If I change the power now to degree 4, there's my basic quartic shape, and again I can still take that same shape and translate it to the left or translate it to the right. Sorry, I just went right when I said left. Translate it to the right or to the left. Okay, in the same way that we saw that happen with the parabola. Then we know, if we have a look at this one, so x to the power of n plus k, so x to the power of n, so outside of the function we add on or subtract a value. So at the moment again n is 2, so we're familiar with our parabola, and we know that when we, sorry, let me close that and open it again. We know that when we increase the value of k, it translates the graph up. We know that when we decrease the value of k, it translates the graph down. Okay, and the same will be true when we change the shape. So if we make it a cubic function, okay, so there's the cubic, and we change the value of k. If k is 6, this is x cubed plus 6. It is just the x cubed graph gone up by 6. Let me just edit the window slightly here so we can just see that the shape's not changing so much. Just let me pause for a second. Okay, so I've just edited that slightly, so hopefully you can see a bit better now that when it goes up, the shape's not changing at all. If you pick any x value, it is simply gone up by 3 units. Up by 3 units, okay? So while it looks like it's getting squashed here, it's not actually getting squashed, it's still up by 3 units. It's just that the slope of it's different, okay? That's also, let's just be clear about that. Sorry, let's just get rid of those annotations. Whoop. Okay, so it can go up or down simply by however much we add on or subtract. So at the moment k is -7, so this is the graph of x cubed minus 7, and the graph has been translated down by 7. So in the same way that the translations, when we're talking about the parabola, the translations allow us to think about where the turning point has moved to. For the cubic, it allows us to think about where the point of inflection has moved to. Right, if I make it a quartic, same thing. If we change the value of k, we're just going up and down. Okay. Alright, and then obviously finally we can put all of that together if we change our value of n, oh sorry, we're in the wrong one again. If we change n now to be the cubic, we can combine all those things together. So we can dilate it a bit, we can then also translate it to the left or right. We can also then translate it up or down, okay, and we can create a whole different cubic function. So just let me just go back to the original graph because I can edit it more easily. So what we, at the moment a is 1, so this is just n is 3, so this is just y equals x cubed. So we already know, let me just have a play around with n. So we already know that when n is 2, sorry, on the wrong screen again. Okay, when n is 2, we know we have the quadratic shape. When n is 3, we have the cubic shape, which we've just met today. When n is 4, we get this quartic shape. When n is 5, we get a shape again that's more like a cubic. But remember I said to you previously, you see it's more extreme. It looks like it's flatter for longer. It's not technically flatter for longer, but it is. It has a very, very small gradient for a longer time. It's closer to the x-axis around that point of inflection. And then it actually shoots off more quickly. It's steeper as well. So if we were to draw the two graphs on the same axis, the degree 5 would be much, much steeper when x is bigger than 1 and when x is less than -1, and it would be less steep, so flatter and closer to the x-axis between -1 and 1. Okay, and same if we go degree 6, it's just a more extreme version of the degree 4. So let me go back to 4. So that was 4. Okay, so remember, there's 2, there's 4, and there's 6. 8, more extreme again. 10, more extreme again. 12, more extreme again. Okay, so we really only have these shapes. Okay, they just get more extreme. Oh, sorry. I've ruined the counter. So just wanted to give you that sense. So all the transformations that we understand from our parabola apply no matter what the degree is. Okay, so we change the degree to 2. From 2, so at the moment on this particular graph it's 2. We change the, let me just fix those other values as well. Let's make k a whole number value. So let's make k -2. Let's make a whole number value as well. Let's make a +3. Okay, so at the moment this is the graph of 3 times x plus 1 squared minus 2. So turning point at -1, -2, and a dilation by a factor of 3. of the parabola. If we were to now change the n value so that it's 3, it's a cubic graph with those same transformations applied. Dilated by a factor of 3 from the x-axis, so it's steeper than the other one. Translated to the left by 1 and translated down by 2, so its point of inflection is at -1, -2. If we were to then change the power, the degree, to degree 4, it is now a quartic shape with the same transformations applied. Dilated by a factor of 3 from the x-axis, so it's taller and thinner. Translated to the left by 1 and down by 2. And so we've got those same things happening. So if we can understand the transformations for the quadratic, we can understand them for these basic cubic and quartic shapes. Okay, we're just starting with a different shape. Okay, I'm going to go back over to the notes. Okay, so we've established our basic shapes. We've reviewed our transformations, which are summarised in this table here for you. So a times x to the power of n, the graph is dilated by a factor of a from the x-axis, and if a is negative, the graph is reflected in the x-axis. X minus h to the power of n, the graph is translated to the left or right. So remember, x minus 2 to the power of n would be translated to the right by 2, and x plus 3 to the power of n is translated to the left by 3. And then x to the power of n plus k, so the k outside of the function, okay, so here the k is outside the function, here the h is inside the function. So the power of n is being applied to it when you're translating left or right. The power of n is not being applied to it when you're translating up or down. So x to the n plus 1 would be up by 1, x to the n minus 4 would be down by 4. So we want to be able to put all those things together to be able to sketch our polynomial graphs of this particular form. In the next video, we'll look at more polynomial graphs. You might remember I said to you right back in the very first video that there's a much greater variety of what can happen with the graph. So not every single cubic graph is this shape. Okay, not all cubics are going to be in that shape. Cubics that can be written in this sort of turning point form will all be in that shape. So if we can write it in that form, it will be this shape. If it can't be written in that form, which is possible for a cubic, then it won't look like this, and we'll meet those other ones in the next video. Okay. Similarly, the quartic will only look like this if it is transformations applied to x to the power of 4. So if the equation can be written in this form. Okay. If it can't be written in this form, then it's not going to be this shape, and we'll meet some other examples of what quartics can look like in the next video. But for now, we're going to focus on these particular ones, so putting together what we know about parabolas with these two new shapes. Okay, sketch graphs of each of the following showing all key features. Okay, so let's think about what's happening here. So our shape here is a cubic shape. Okay, it has been dilated by 2 from the x-axis. I suspect I should have left us some more space here, so just write a bit small. So that's that 2 there, and then this plus 2 here means it's gone up by 2. So the point of inflection. The graph hasn't translated to the left or right at all, so the x-coordinate will still be at 0, but it has gone up by 2, so the point of inflection is now at 0, 2. Okay, so our graph is going to do something like this. Point of inflection will be at 0, 2. Okay, it is going to do this. Now, like a parabola, minimum amount of information, at least 2 points, including the point of inflection. Okay, so our graph is going to look something like that, 0, 2, and also all axis intercepts must be marked. So we're going to clearly need an additional point, but we also need to mark this x-axis intercept, so that's the point we're going to need to calculate. So let's work out the x-intercept. So we do that by letting y equal 0. That doesn't change for a cubic, that's true for all functions. And then whenever we're solving cubics that are in this particular form, we're only ever going to have x in one place, so we can always solve it by rearrangement. So we're going to subtract 2. We're then going to divide by 2, so -1 equals x cubed. And then we're taking the cube root of -1, which is -1. Okay, now remember, when you take a cube root, you don't get plus minus, because when we cube a negative, we get something negative. When we cube a positive, we get something positive. So therefore, if we're taking the cube root of something negative, it must have been a negative thing that we cubed. Okay, so that is the point -1, 0. So minimum 2 points, including the point of inflection and all axis intercepts. Okay. All right, good. Okay, let's have a look at this one. Let's start off with the shape. It's a quartic graph, but also I'm noticing that it's been reflected. So it's a reflected quartic graph, so the shape is going to be going this way. So the sort of flat-bottomed parabola. It's not a parabola, but compared to the parabola, more flat-bottomed. Yeah, that's the reflection in the x-axis we've also shown in the shape. Okay. Then we've got this -1 in here, which moves the graph, translates the graph to the right by 1. So in terms of it's not a point of inflection here, it's a turning point. So the turning point, we've gone to the right by 1, so the x-coordinate of the turning point will now be at 1. We have not translated up or down, so the y-coordinate of the turning point is 0. We can think about there being a +0 on here if we need to. Okay. Alright, so it's this shape to the right by 1, so that turning point is going to be at 1, 0, which is also obviously the x-intercept. We're then going to have this sort of quite steep and flat-bottomed shape. It's not the best quartic I've drawn, but we'll go with that. And then remember, minimum information, turning point and at least one other point, plus all axis intercepts must be marked. So we need to calculate another point, and we also need that y-intercept, so let's calculate that. So y-intercept for all graphs is when x equals 0, what does y equal? Okay, so it's negative 1 to the power of 4. So negative 1 to the power of 4 is positive 1, but then this negative out the front here means that it'll still be negative. That marries with what we're seeing with our graph. And so that's the point 0, -1. Okay, let's have a think about this one. So y equals x to the power of 4, not reflected. Okay, so our shape is going to be the quartic shape. Okay, and all that's happened to it is this -6 out here, is it's gone down by 6. So the turning point hasn't gone to the left or right, so it'll still have an x-coordinate of 0, but it's gone down by 6, so it'll be at 0, -6. Okay, so let's think about what's happening there. Turning point's going to be down here. We're going to have this sort of flat-bottomed quartic shape. It's symmetric about the y-axis because we haven't gone left or right, so I do want my drawing to sort of reflect that if I can. So that is 0, -6, both y-intercept and turning point. We need at least one other point, but we also need to mark all axis intercepts, and there are 2 x-intercepts here, and so we need to calculate those. So x-intercepts are found by letting y equal 0. And we can always solve these sorts of equations simply by rearranging, so doing the same thing to both sides until we get x on its own. So we're going to add 6, and then we're going to take the 4th root of 6. Okay, or you might choose to write that as 6 to the power of a quarter, which is the same thing obviously. Now when we take an even root, sorry, my mistake, plus or minus 4th root of 6. That's why we've got those 2 x-intercepts. Now it doesn't really matter how big that is. I'm just going to label my x-intercepts as the 4th root of 6, 0, and the negative 4th root of 6, 0. Now you might like to think, obviously, the 4th root of 1 is 1, and let me think about 2 to the power of 4 is 16, so the 4th root of 16 would be 2, and so the 4th root of 6 is going to be somewhere between 1 and 2. Probably closer, definitely closer to 1 than it is to 2. Be careful when you write a 4th root that it doesn't look like 4 times the square root of 6. Okay, so it is the 4th root of 6, and that's why sometimes perhaps using fractional indices might be a neater way to write that, 6 to the power of a quarter. So we might choose instead to label our x-intercepts as 6 to the power of a quarter, 0, and -6 to the power of a quarter. Either way, it's fine, whatever suits you. But again, you want to try and get that symmetry, that bit more flat bottom shape, so we can distinguish this as being a quartic as opposed to a quadratic, and all axis intercepts and turning points. Okay, question 4, -x plus 2 cubed plus 8. Okay, so we've got a cubic and it's reflected. So that means that the shape is going to be a reflected cubic, so it's going to go down as we go from left to right. We've also gone to the left by 2 and up by 8. So together, those two things mean, sorry, I was going to write turning point, it's not a turning point, our point of inflection is going to be left 2, so negative 2, and up 8, positive 8. Okay, so let's have a think about what we've got happening there. So negative 2 and 8. So it's going to be sort of, right up here somewhere, that point of inflection. And then my graph's going to go this way. Don't draw this in just yet. So it's going to cross the y-axis somewhere, it's going to cross the x-axis somewhere. Now, I drew it a particular way because I made certain assumptions, but it's possible that it might cross down here and have a negative x-intercept and a negative y-intercept. So let's make sure that we calculate those values first. The other thing is, we've now indicated on our y-scale that that value is 8 and that that value is negative 2. Okay, so we now, and our x-scale we've also indicated. So we now need to make sure that any other points we draw on here are relatively accurate. So for example, if the y-intercept turns out to be at 2, we don't want that to be up here. Okay, so it's important that we calculate the values before we actually mark the draw the graph in. Sorry. Okay, so let's calculate our y-intercept to start with, because that's easier. Y-intercept is when we let x equal 0, so y equals negative, it'll be 0 plus 2, so that's 2 cubed plus 8. Okay, so that's negative 8 plus 8. Now actually the y-intercept is 0, which means the x-intercept is also going to be 0. So we don't need to calculate another point. We can see now what's going to happen here. So try and get that sense of a moment of 0 gradient before it then turns around again to come through this point at the origin. Now the origin you don't technically need to label with coordinates, but given it's the only other key point on the graph, I'm going to be clear about what's happening. Okay, so some work to do here, so putting together those two new basic shapes along with our knowledge of transformations in order to sketch some basic cubic and quartic graphs. In the next video, as I said, we'll explore further what if it's not this particular cubic shape or this particular quartic shape, and how can we sketch that and how can we know that.